Exam prep module 4, propagation, antennas, and feed lines. And it says here 4.1's propagation, antenna and radio wave basics, feed lines, and SWR, which is standing wave ratio, and practical antenna systems. Radio waves propagate in many ways depending on the frequency of the wave and the characteristics of the environment. We'll discuss 3 basic ways: line of sight, ground wave, and sky wave. Line of sight. Radio energy can travel in a straight line from a transmitting antenna to a receiving antenna, called the direct path. There's some attenuation of the signal as the radio waves travel due to spreading out. This is the primary propagation mode for VHF. For VHF and UHF, sorry, I had an interruption there. Radio waves can be reflected by any sudden change in the path they are traveling, such as a building, hill, or even weather-related changes in the atmosphere. Vegetation can also absorb VHF and UHF radio waves. Precipitation, such as fog and rain, can absorb microwaves and UHF radio waves, although it has little effect on HF and lower VHF bands. Ground wave. At lower HF frequencies, radio waves can follow the Earth's surface. These waves travel beyond the range of line of sight. Range, a few hundred miles. That really depends on power. The primary one that I think of with ground wave is a AM broadcast band. Reflect, refract, and diffract. Radio waves are reflected by any conductive surface, ground, water, or buildings. Refraction, or bending, occurs when waves encounter a medium having a different speed of light, such as water or an electrical feed line. By bending signals back towards the ground, refraction counteracts the curvature of the Earth and allows signals to be received at a distance beyond the visual horizon. Knife edge diffraction. Diffraction is waves travel past sharp edges of large objects. Multipath. Radio signals arriving at a receiver after taking different paths from the transmitter. Results in irregular fading even when reception is generally good. One of the times this happens is when you're driving through town and you're getting refracted signals from different buildings which are sharp corners and usually have metal in those corners to really help with that. Because dead spots for multipath are usually spaced about a half wavelength apart, VHF or UHF signals from a station in motion can take on a rapid variation in signal strength known as mobile flutter or picket fencing. And that's also why Randy tells you that if you're not getting well, to move over a foot. Distortion caused by multipath can also cause VHF and UHF digital data signals to be received with a higher error rate, even though their signals may be strong. Tropospheric propagation. Propagation at and above VHF frequencies are assisted by variations in the atmosphere. Variations such as weather fronts, temperature inversions, create layers of air next to each other that have different characteristics. The layers form structures called ducts that can guide even microwave signals for long distances. Regularly used by amateurs to make VHF and UHF contacts that would otherwise be impossible. Line of sight propagation that would be impossible by line of sight, 300 miles or more when using ducted propagation. Practice questions. Why do VHF signal strengths sometimes vary greatly when the antenna is moved only a few feet? The answer is C. Multipath propagation cancels or reinforces signals. What is the effect of vegetation on UHF and microwave signals? The answer is B. Absorption. What is the meaning of the term picket fencing? And the answer is B. Rapid flutter on mobile signals due to multipath propagation. What weather conditions might decrease range at microwave frequencies? The answer is C. Precipitation. What is a likely cause of irregular fading of signals propagated by the ionosphere? D. Random combining of signals arriving by way of different paths. What effect does multipath propagation have on data transmission? And the answer is D. Error rates are likely to increase. What is the effect of fog and rain on signals in the 10-meter and 6-meter bands? B. There's little effect. It's the higher VHF and UHF frequencies that mainly are affected. What type of propagation is responsible for allowing Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations? The answer is A. Knife edge diffraction. I think Harry gets that across the Blue Ridge. What type of propagation is responsible for allowing over-the-horizon VHF and UHF communications to ranges of approximately 300 miles? And it's A. Tropospheric ducting. What causes tropospheric ducting? And the answer is D. Temperature inversions in the atmosphere. Why is the radio horizon of VHF and UHF signals more distant than the visual horizon? C. The atmosphere refracts radio waves slightly. The ionosphere. 30 to 260 miles above the Earth's surface is the ionosphere. Atmosphere thin enough for atoms to be ionized by solar ultraviolet radiation. Ions are electrically conductive. Because of varying density, the ionosphere forms layers with different amounts of ionization. Ionization varies with solar illumination, hourly, and intensity of solar radiation. Higher ionization refracts or bends radio waves more strongly. Ionospheric layers. Layers D, E, F1, and F2. Depending on whether it is night or day, and on the intensity of solar radiation, these layers can refract E, F1, and F2 layers, or absorb D and E layers radio waves. Each reflection from the ionosphere is called a hot. It can go hundreds or thousands of miles on a hot. And one of the things, if you remember, they said water could diffract or reflect. And one of the things that controls hops is if you have something reflective where the hop bounces from next, and is especially effective over the ocean, although it may be affected by storms, which would make the sea rougher. Sunspot cycle activity. The level of ionization depends on the intensity of radiation from the sun. Radiation from the sun varies with the number of sunspots on the sun's surface. High numbers of sunspots results in high levels of ionizing radiation emitted from the sun. Sunspot activities follow an 11-year cycle. F layers can reflect 6 meter, that's 50 megahertz signals, at the sunspot cycle's peak. Patches of the E layer can become sufficiently ionized to reflect VHF and UHF signals. This is called sporadic E, most common during early summer and midwinter months on 10 and 6, and occasionally on 2 meters. The ionosphere, an RF mirror. Ionosphere can refract radio waves back to Earth. Acts like refraction. Most refraction occurs in the F layer. Refraction depends on frequency and angle of incidence. Too high a frequency or angle and the waves are lost to space. More in the ionosphere. The highest frequency signals that can be reflected back to a point on Earth between the transmitter and receiver is the maximum usable frequency. Sky waves or skip propagation is responsible for most over-the-horizon propagation on HF and low VHF, 10 and 6 meters, during peaks of the sunspot cycle. Skip is very rare on the 144 megahertz or higher UHF bands. E regions of the ionosphere is also home to meteor trails. Bouncing signals off of these ionized trails is called meteor scatter propagation. The best band for meteor scatter is 6 meters, and contacts can be made at distances up to 12 to 1,500 miles. And most often occurs between midnight and noon, because that's the time that the part of the Earth is heading in the direction for the meteors to be overhead or near you. Practice questions. Which region of the atmosphere can refract or bend HF and VHF radio waves? And the answer is C, the ionosphere. Why are simple UHF signals rarely heard beyond their radio horizon? And the answer is C, UHF signals are usually not propagated by the ionosphere. What is a characteristic of HF communication compared with communications on VHF and higher frequencies? The answer is C. Long distance ionospheric propagation is far more common on HF. What is the characteristic of VHF signals received by aural backscatter? B, they are distorted and signal strength varies considerably. Which of the following types of propagation is most commonly associated with occasional strong signals on the 6, 10, and 2 meter bands from beyond the radio horizon? And that would be B, sporadic E.
Howard,
Yes.
go back to that last question just a second. I didn't see it come up, and it may come up later on, I'm not sure. But you might want to explain what gray line propagation is.
All right. Gray line propagation occurs at sunrise and sunset, and it seems that at this time you can communicate around the Earth to other locations that are also on the gray line. And in the wintertime, the gray line is grossly different from that it is in the summertime. Right after, right at spring and fall, the equinoxes, the gray line is pretty much straight up and down, but it's curved due to the fact that the North Pole is in darkness during our summer, and the South Pole is in darkness during our winter, and the gray line moves considerably during that period of time. It's easier to get into Asia in the summer because of this.
Howard, part of what's going on there is as the Earth is turning around, the ionosphere is changing. When it's dark, I think that refractive layer is closer to the ground, and when it is in daylight, it's further away. And so when you look at the part of the world where the sun is shining on it, it's kind of like you've taken your mirror and put a step in it. Mirror is not a good word for refraction, but you get your signal is maybe bouncing off a surface which is not uniform, and so you get some interesting things happen there.
Yes. All right. What band is best suited for communicating via meteor scatter? That would be B, 6 meters. What is generally the best time for long distance 10-meter band propagation via the F region? And A would be from dawn to shortly after sunset during periods of high sunspot activity. When the activity gets really high, it will stay open, meaning you have a long distance communication for a little bit after your sunset and a little bit before sunrise.
And that's because the sun is exciting the ionization in the ionosphere during those hours.
Yes, and what it is, it's always exciting the ionosphere, but it's the part the part that's in daylight is over you, and that's when or between like us and Europe. And if you want to talk to Europe, you're best when that area is highly ionized. Does that make sense?
Yes, it does. Thank you.
Okay, by the effort. We got that one. Let's go on. Which of the following bands may provide long distance communication by the ionospheric F region during the peak of the sunspot cycle? And that would be A, the 6 and 10 meter bands. Not to mention the 160 up to 10 meters. All of those are enhanced during that period of time. But the answer for our question here is the 6 and 10 meter bands. Antenna radio wave basics. The antenna system. Antenna transforms current into radio waves, or transmits, and vice versa during receive. The feed line connects your station to your antenna. Test and matching equipment allows you to monitor and optimize antenna system performance. And for an antenna to do that, for the antenna to do that job efficiently, its dimensions must be an appropriate fraction of the signal's wavelength. Radio wave.
Excuse me.
Yes, I'm sorry.
That's okay. Would you mind defining station as it's being used there?
Okay, station is your transmitting equipment and receiving equipment. That is your station. Does that make sense?
So your radio and everything that's connected to the antenna?
Yes. Like if it's a handheld radio and the antenna is connected, and that could be your station, just a handheld radio. It could also be a big radio, a amplifier, your matching equipment, your coax, your tower, your antenna. The whole ball of wax could also be your station. It's just what you are using, but that's like in the old term, a radio station or a TV station.
Can y'all
Great.
see that?
Yes.
Okay, that's my HF station.
Oh, hold on. Go ahead then.
Yeah, the top parts, the display, this station's in two pieces. The next one down with the red light is the tuner. Then the one below that's the main body of the transformer receiver. So this is a HF station. You can't see the coax because the coax is in the back. And
Okay.
the power supply is down here under the desk. So that's a station.
Okay, thank you.
All right. The radio wave is an electromagnetic wave that contains both the electric and magnetic energy or fields created by the RF current. I'm going to explain that just a little bit more. When an electrical current moves in an antenna, and if you remember our sinusoidal wave that we were looking on Rick's equipment that was up and down, this is our RF signal entering the antenna, and this causes current to flow. As that current builds up in the antenna, it creates a magnetic field, and as it collapses, it is as the magnetic field collapses, it creates an electrical field. And as that electrical field collapses, it creates a magnetic field. Now it's moved away from your antenna, and yet that magnetic field is still building up and collapsing and generating the electrical field, which is building up and collapsing and generating the magnetic field. And this is kind of how it works. And it goes on forever. It just gets weaker and weaker. And since light is also an electromagnetic wave, you can see light from distant stars that's been transmitted millions of years ago. But that's how the electromagnetic waves seem to work. The electric and magnetic fields are at right angles to each other and oscillate at the same frequency as the RF current in the antenna. Antenna vocabulary. Element. The conducting parts of an antenna designed to radiate or receive radio waves. Driven element. The element supplied directly with power from the transmitter. That's where the coax is connected. Array. An antenna with more than one element. A parasitic element. Elements not connected directly to the feed line. Resonant. An antenna is resonant when its feed point impedance has zero reactance. Feed point, where the transmitted energy enters the antenna. Radiation, not radioactivity. An antenna emitting electromagnetic waves. Electromagnetic waves. Radio waves are electromagnetic waves. Electromagnetic fields at right angles to each other oscillating at the wave's frequency. Sprout out into space from the antenna. Created by the AC current in your antenna. Wave and current have the same frequency. Wave polarization refers to the orientation of the radio wave's electric field. Vertical or horizontal, determined by the elements. Can be circular if the orientation twists as the wave spreads through space. Combinations of polarization are called elliptical polarization. Both vertical and horizontal antennas are effective for receiving and transmitting on the HF bands where skip propagation is common. When the polarization of transmit and receive antennas aren't aligned the same, the received signal can be dramatically reduced. Less current is created in the antenna. Summary: antenna and wave polarization must match for the maximum reception. Practice questions. Any questions at this point? Okay. What happens when, What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? The answer is B. Received signal strength is reduced. Which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? And the answer is B. Either vertically or horizontally polarized antennas may be used for transmission or reception. What is the relationship between the electric and magnetic fields of an electromagnetic wave? They are at right angles. Something that you'll never see, but they are at right angles. What property of a radio wave defines its polarization? The orientation of the electric field. That's A. What are the two components of a radio wave? The answer is C, electric and magnetic fields. Antenna, some vocabulary. Gain, apparent increase in power in a particular direction by focusing radiation in that direction. This is measured in decibels, which is a logarithmic term. Isotropic, equal radiation in all directions. And omnidirectional, no preferred horizontal direction. Directional, an antenna that focuses radiation in a specific directions. Okay, this are antenna radiation patterns. And this is a display, and the one on the left is as if you're looking down on the antenna from above and shows the horizontal plane, whereas the one on the right is the elevation pattern. I believe that's called a cardioid pattern, and we won't go into the type of antenna with that right off the bat, but if you can see, you can get software that will show you this for any antenna that you want to think up and design, and I use that. It's a lot of fun because you can design an antenna in the computer before you ever touch a piece of wire or something and give you ideas about what's going on. Antenna radiation patterns. Radiation patterns are a way of visualizing antenna performance. The further the line is from the center of the graph, the stronger the signal at that point. Graphs are calibrated in decibel. Most common type of radiation pattern is an azimuthal pattern that shows the antenna's gain in horizontal directions around the antenna. An elevation pattern shows the strength of the radiated energy in vertical directions as if the antenna is viewed from the side.
Was that example diagram possibly of the same antenna, just from different viewpoints?
That's exactly what it was. You wish to go back?
Yeah, just for a second, if we could take a look at it so I can understand.
Okay, take me a second. So this antenna, I think, is set up with a feeding two verticals that are about a quarter wave apart. In one direction they cancel, and in the other direction they are enhanced. And so you're not really usually all that interested in how much up you're getting with your antenna, because that's probably going to go right on out into space. And the horizontal is what you're really interested in, because if you're wanting to talk to George across town, then you want to point your antenna where your maximum signal is in his direction. There are also times when you're trying to work a station and you have interference that you're receiving.
Oh, yeah. Okay.
And if you turn your antenna so that that notch on the left is in the direction of the station causing you interference, you can minimize the interference in your receiver.
Oh,
Which
yeah.
is
That's a really
also
good
quite
point. Yeah.
useful. And then on the right, that's again your elevation pattern, and primarily where you'd be interested in that is if you're trying to work skip, where you're refracting your signal off the atmosphere. The lower that elevation angle, the farther out you're going to impact the atmosphere, and therefore the longer the skip you're going to get.
Oh, I see. Yeah. Okay. So like the lobes, looking at the elevation pattern, like the lobes that are at 10 o'clock and 2 o'clock, they're the ones that you're most interested in because you'll get a sort of a lower angle of attack on the ionosphere.
Exactly.
I
And
see.
that
Okay.
big lobe that's pointing straight up, that's not quite as strong, that's all going to go out into space and not help you much.
I see. Okay. Thank you very much.
You're welcome. Anytime.
What direction are you looking at the elevation from?
You're looking at it from, let me back up. You're looking at it from the ground as if this antenna is a vertical, and you're just standing there looking at it. Does that make a sense? You're looking at it from the side on the right, and on the left, you're looking down at it from above.
But what point on the clock are you looking at it? I guess I'm trying to compare the two. You know, at what point on the azimuthal pattern are you looking at the elevation pattern? What direction? From what direction are you looking at the elevation pattern?
That's a good question, and it could be somewhere in the 0 degree angle.
It's not direction as in east or west. You're looking at it just from the side to see whether it's radiating more up or more horizontal.
And you can also get three-dimensional, but this is kind of a poor example because I can't tell you which angle that's looking at from, but you would think that from that horizontal display, if you were looking at it from the 270 degree angle, you wouldn't see near as big a lobe in the back as the front. So I'm not sure where that view came from. However, in your software that will do that, you can pick what angle you want to look at something from. And you can also get a three-dimensional view of it. And
Okay, thank you.
if we get through early enough, we might try some of that. Or maybe at a different night. Now, did I cover this? Nulls? No, I don't think I did. Radiation pattern vocabulary. Nulls are the directions of minimum gain. Lobes, the regions between nulls. The main lobe with the highest gain, main lobe is the lobe with the highest gain. Side lobe, any lobe other than the main lobe. Forward gain, gain in the direction assigned as forward. Azimuth pattern, radiation pattern showing gain in all horizontal directions around the antenna. Elevation pattern, radiation pattern showing the gain at all vertical angles from the antenna, often restricted to angles above the horizon. Front to back ratio, Ratio of forward gain to gain in the opposite direction. Front to side ratio. Ratio of forward gain to gain at right angles to the forward direction. Now we get into the decibels. And in this case, this is pronounced dB. A ratio is expressed as a power of 10 to make large numbers easier to work with. Decibel measures the ratio of
Hey,
two
Howard, can
quantities.
I?
Go ahead, Rick.
Yeah, before it gets dark, I would wait till the end of class otherwise, but before it gets dark, can you guys see me? Or, I mean, can you see what I'm doing?
I can't.
All right. Why is that not showing up? It says I got video running. Can you,
If you have the view where you can see whoever's talking, then you can see Rick outside.
I understand.
can you share it for just a minute?
Well, if you're talking, they can see you.
Okay.
I can't, but they can.
All right. What I have here in front of me is a directional experimental antenna that I built a while back. This one's called the Yagi. Couple of things I just want to cover on antennas that can be a little confusing. This element, the metal piece is this way. I got to get a better grip on this thing. That would be horizontal orientation or horizontal polarization. This is vertical polarization.
Hey, Rick, the camera's facing you, not the antenna.
Well, now, doggone it. How about that? Can
There you
see?
go. There you go.
You
I
look
tried-
good, though.
I selected the front camera, but it's not showing you. Okay. This is vertical polarization. This is horizontal polarization. The far end of this antenna is the front. That is where most of the radiation goes, is off that end of the antenna. So where you point it is where most of the radiation power goes. So drop that back on the ground. But that's just an easy way, whichever way the elements are rotated, pointing up, down, or east, west, or left, right, whatever, that gives you your polarization on the antenna. Like I said, this antenna is very directional. You take the one mounted on top of my car. Let me walk over here to the Tahoe. Can you see that antenna? That's a vertical antenna. It's vertical polarization.
Yeah, just like this one right here. This is a mag mount mobile antenna.
And it is non-directional or omnidirectional, depending on which way they want to say it. But it comes down to the same thing. It radiates equal power all directions around the vehicle. So, yeah, I just wanted to cover that before it got dark, Howard. I'm done. Back to you.
All right. When I'm talking, you are seeing the display of the slides, aren't you? Somebody answer.
Yes.
Okay. I just want to make sure that you weren't seeing me and not seeing that, but okay. Decibel measures the ratio of two quantities as a power of 10. And you can just look this up in a log table, find it on a slide rule, do it with a calculator. If you're talking about the power ratio, it's 10 times the logarithm. And if you're talking about a voltage ratio, it's 20 times the logarithm. And again, those are measured in dB. Positive values in dB indicate ratios greater than 1, and negative values of dB are for ratios less than 1. And everything we're talking about, we can get a lot deeper into, but right now, this is what you need to know for this lesson. Antenna gain is discussed in terms of dB. Now we go to practice questions. What is antenna gain? And the answer is C. The increase in signal strength in a specified direction compared to a reference antenna. Usually they use either an isotropic antenna, which closely would resemble a light bulb if the light bulb did not have a support and just radiates in all directions. The sun is an isotropic source. It radiates in all directions. The other thing that they refer it to is a dipole. So you will see those terms as in dBd or dBi. And there's about, I think, 2.7 dB difference between it. So some people like to use the dBi because it looks better than the dBd. But if you know what they're talking about, you realize that they're the same. Which decibel value most closely represents a power increase of 5 watts? And that is B, 3 dB. If you double the power or half the power, it's 3 dB. Which decibel value most closely represents a power decrease from 12 to 3 watts? That would be C, minus 6 dB. If we take 12 and divide it in half, for 3 dB is 6 watts, divided in half again for 3 watts. So that would be 3 dB each time. That's 6 dB. Which decibel value represents a power increase from 20 to 200 watts? The answer is A, 10 dB. 10 dB is equal to 10 times. Any questions about dB now before we move on to feed lines? I know that's probably clear as mud, but those are the numbers that right off the top of your head, if you see an antenna advertised that's a mobile antenna mag mount to go in your car, and it says that it has 5.3 dB dBi, you know that that's how much gain that you get over the isotropic source. If it's dBd, it's that much gain over a dipole. The purpose of the feed line is to get RF power from your station to your antenna. Basic feed line types: coaxial cable, called coax, and open wire line, also called ladder line or window line. Power lost as heat in the feed line is called loss, and it increases with frequency. Feed lines used at radio frequencies use special materials and construction methods to minimize power being dissipated as heat by feed line loss and to avoid signals leaking in or out. Feed line vocabulary: the center conductor. And we'll look at the top left-hand picture on the right there. That shows the center conductor, then dielectric, is what's around the center conductor. The shield, which is a braided or foil surrounding the dielectric. Jacket is the protective outer coating. Forward or reflected power is RF traveling toward or away from a load such as an antenna. And just a little more about the coaxial cables there. They're showing different types, and in general, the one on the bottom right is the best. And then probably that double shielded is, well, no, I guess the rigid hardline's best. And then the semi-rigid hardline, the semi-flexible, and then the double braided, and then the single shielded. And we're going to look at them closer, I guess.
I start saying, we weren't looking at what you were looking at, Howard. You were looking at the next slide window.
I was looking at the next slide window. I apologize. But again, the center conductor, the dielectric, that can be made up of a solid plastic or a plastic that has air bubbles in it that they call foam core. And then you have your outer conductor, which is your braid, usually braided copper, sometimes silver plated braided copper. And then there are some where they wrap full and then put the braid over that. And then your rigid hardline is a stiff pipe type thing, and usually it just has spacers in it where most of what's inside of it is air. And the semi-flexible has a corrugated shield, so it's easier to bend without kinking and therefore shorting your center conductor to your shield. I'm sorry. Coaxial cable continued. It's the most common feed line. It's easy to use. Carries the radio signals on the surface of the center conductor and the inside of the surface of the outer shield. And it's not affected by nearby materials because the signal is protected by the shield. Has higher loss than open wire line at most frequencies. Air insulated hardline has lowest loss, but limits the amount of bending that you can do with it. And this is open wire line. If you ever remember having before they went to digital TV, external antenna, that 300 ohm twin lead was the common used feed line for that. And that 450 ohm window line is the type that's out there. And you can actually make this yourself if you use two wires, and there's a formula you can use to use the proper spacers to space them apart. I think you can buy one made like that, so it's 600 ohms, but you can set, but according to the size of the wire that you use, there's a spacing that will make the impedance that you wish to have your line. I visited the Voice of America station in Greenville, North Carolina, the last one that's operating. And I think they used 1.25 inch copper pipes on top of telephone poles, separated by about a foot, 1.5 feet for an open wire feed line. Of course, they're running 500,000 watts out to, I think, so you need something that can carry 500,000 watts.
Howard?
Yes.
I saw before Channel 13 went to digital, we went up there and I saw the coax that they were feeding their antenna with.
Yes.
And it was a piece of brass pipe, probably about 8 inches in diameter. And the inside of it was maybe a 2 inch brass pipe, and it had ceramic spacers And the pieces were about 6 feet long. I didn't see how they joined the inside, but that's what you were talking about, that airspace coax.
Yes.
Now, I don't know how many megawatts they were using up there. Did get into that, but that was a piece of coax. And then you can't see it, but I've got a piece of RG316 here laying here that I evaporated the outside of doing something that I don't understand. And it's maybe 3/32 of an inch in diameter.
Yes. Okay. Open wire line is lighter and less expensive than coax. Lower loss than coax at most frequencies. More difficult to use since it is not shielded and is affected by nearby materials. If you run it next to something metal, it will affect it. Requires impedance matching equipment to use with most transceivers. Open wire feed lines cannot be buried or installed in metal conduits and must be kept clear of nearby conductive surfaces. However, it's really good stuff to use if you can get around all of those problems. Characteristic impedance. The impedance presented to a wave traveling through a feed line, given in ohms, symbolized as Z0. Depending on how the feed line is constructed and what materials are used, coax 50 and 75 ohm are the most common, but they have a lot of other impedances out there. Open wire line 300, 450, and 600 ohms. And again, you can make whatever you need. Most coaxial cable can be used in ham radio as a characteristic impedance. Most used as a characteristic impedance of 50 ohm. It's the most common. That's what our radios are designed for. Standing wave ratio. If the antenna feed point and feed line impedances are not identical, some RF power is reflected back toward the transmitter. This is called a mismatch. Forward and reflected waves create a pattern of standing waves of voltage and currents in the line. SWR is the ratio of SWR ratio is the ratio of standing wave maximum to minimum voltages. Measured with an SWR meter or SWR bridge. SWR continued. Reflected power is re-reflected at the transmitter and bounces back and forth. Some RF power is lost to heat on each trip. On each trip through the feed line. All RF power is eventually lost as heat or transmitted to the antenna or load. Transferred to the antenna or the load. In other words, most of it still gets out. The problem is it interferes with the final output of the transmitter. High SWR means more reflections and more loss of RF power, less transferred to the antenna or load. SWR equals the ratio of feed point or load and feed line impedance, whichever is greater than 1. And SWR is always greater than 1. What is an acceptable SWR. 1-to-1 SWR is perfect, no power reflected. Up to 2-to-1 SWR is normal. Modern radios lower transmitter output power for protection when SWR is above 2-to-1. And if you remember, they said that when an antenna has no impedance is when it's resonant. And an antenna can only have no impedance at one frequency. So an antenna that's set up to have perfect SWR in the middle of a ham band, anywhere else in the band, it won't have a perfect one-to-one SWR. So SWR is pretty much always with you unless you design the antenna and feed line for exactly the frequency you want to use, which is what all commercial things are usually done. Again, SWR above 3-to-1 is considered high in most cases. Erratic SWR readings may indicate a faulty feed line, faulty feed line connectors, or a faulty antenna. Something to check out. High SWR can be corrected by tuning or adjusting the antenna with impedance matching equipment at the transmitter called antenna tuner or a transmit match. But again, the antenna tuner or transmatch at the transmitter does not affect the antenna or the feed line. It only makes the transmitter happy. Does not change the SWR in the feed line. Now, back into questions. What happens to power lost in a feed line? And the answer is, it is converted into heat, C. What is the most common impedance of coaxial cable used in amateur radio? B, 50 ohms. Why is coaxial cable the most common feed line for amateur radio antenna systems? A, it is easy to use and requires few special installation considerations. What happens is the frequency of a signal in coaxial cable is increased? D, the loss increases. And I have a radio here that operates at like 1,296 megacycles. This is a frequency that you can use with your license. It would be really easy to dissipate 90% of the power in the coax before it ever reaches the antenna. And you don't have that much to start with. So, which of the following types of feed line has the lowest loss at VHF and UHF? That's C, air insulated hardline. Seldom you see it used, and it's very expensive. But the question answer is air insulated hardline. Which of the following should be considered when selecting an accessory SWR meter? A, the frequency and power level at which the measurements will be made. If you get an inexpensive SWR meter, it might be fine at 10 watts or 100 watts, but if you use 1,000 watts with it, it's probably going to just let all that blue smoke out. What reading on an SWR meter indicates a perfect impedance match between the antenna and the feed line? And the answer is C, 1:1. Why do most solid-state transmitters reduce output power as SWR increases beyond a certain level? And the answer is A, to protect the output amplifier transistors. What does an SWR reading of 4:1 indicate? D, an impedance mismatch. What is a benefit of low SWR? B, reduced signal loss. What can cause erratic changes in SWR? B, loose connection in the antenna or feed line. What is standing wave ratio, SWR? And the answer is A measure of how well a load is matched to the transmission line. Practical antenna systems. The dipole. Simplest type of antenna. A dipole means two electrical parts, two poles. Made from a straight conductor of wire, 1/2 wavelength, 1/2 lambda there, long, with a feed point somewhere along the antenna. Most are oriented horizontally, particularly on the lower frequency bands, and radiate a horizontal signal. Can also be installed vertically, sloping, or even drooping from a single support in the middle, and that's called an inverted V. The radiation pattern isolated in space looks like a donut. If you look at it from the side, as we were looking at that other antenna display a while ago, it looks just round. It radiates in all directions in the vertical frame, and it radiates in a figure 8 pattern in the horizontal. However, just because the end of your dipole is pointing at a station does not mean you can't work it. It just means that it won't have as strong a signal because of the way it's oriented. Ground plane antennas. Most common type is 1/4 wavelength long, 1/4 lambda, with a feed point at the base. Acts like 1/2 of a dipole, with the missing portion made up by the electrical mirror formed by the ground plane. Made from sheet metal or a screen of wires called radials that extend out from the base. In a mag mount mobile antenna, that sheet metal is the roof of your car. Extended length of a 5/8 wave ground plane focuses more of the energy toward the horizon and has better range. And because it focuses it toward the horizon, it has some gain. To reduce the physical size of the antenna, it is often constructed with some of the radiating conductor wound into a coil, or a separate inductor inserted in the antenna is called inductive loading. And here we have a picture of the conductive ground plane for the ground plane antenna. On the left there, the wire with the 3 dog bones is a dipole. That one looks like it's probably fed in the middle because that's where that middle dog bone separates it. And then to the right is a ground plane with, they call that a counterpoise. Counterpoise is always the other half of your antenna. That metal sheet is the ground plane. It's also the counterpoise. And the counterpoise can be made on an HF antenna by radials on the ground or elevated slightly above the ground. A lot of times you'll put them high enough where you can mow under them, or they have a little clip, looks like a hairpin, where you stick them down to hold it where the lawnmower won't hit them. The reason for that counterpoise in the upper right angle down a little bit is because it does impedance matching that way, so that it will better match to a 50 ohm line. Let me get a sip, I'm sorry. Antennas for handheld radios. The flexible antenna used with most handheld radios is called a rubber duck. It's a ground plane antenna shorted by coiling the conductor inside a plastic coating. It does not transmit or receive as well as a full-size ground plane antenna. For best performance, hold the transceiver so the antenna is vertical. They're not very effective inside vehicles, up to 20 times less effective than an external mobile antenna, because all that metal is shielding. Easy to connect handhelds excuse me, to full-size antennas. Uses standard RF connectors. A 5-watt handheld can easily reach 10 miles with a good antenna. Calculating antenna length, the dipole. To calculate the length of a resonant dipole, 1/2 wave long, the length in feet is equal to 468 in megahertz divided by the frequency in megahertz. In other words, 468 divided by your frequency. Example, at 50.1 megahertz in the 6-meter band, the dipole length is calculated as 468 divided by 50.1 is 9.33 feet, equals 112 inches long, which is approximately 3 meters. The value of the constant used in the formula accounts for effects that cause an antenna to act like it is a little longer electrically than it is physically. The actual resonant length is affected by the height above ground, its electrical properties, and nearby conductive objects. So, make the dipole a few percent longer. Use 490 instead of 468. Then use a SWR meter or antenna analyzer to determine the resonant frequency. Assuming the resonant frequency is too low because the dipole is too long, shorten it until the dipole is resonant at the desired frequency. And that's the best way of adjusting that antenna. And you know, if you have something 30 foot in the air, that means you drop it and shorten it and put it back up and test it again, and so forth and so on until you're happy with it. all the things that you see about making antennas, generally, that's the way you end up doing it. Calculating ground plane length. The length of a ground plane antenna is half of a dipole and is often estimated as the length in feet equals 234 divided by the frequency in megahertz. Example, at 146 megahertz, a lambda divided by 4 ground plane is 234 divided by 146 equals 1.6 feet long equals 19 1/4 inches. Length adjustments also apply, similar to previous note about dipoles. Directional antennas. Simple dipoles, ground planes, and loops work well, but they have little gain. Radiation patterns don't have strongly preferred directions. Use a directional beam antenna and get the best reception in one direction. And if I haven't said it, antennas are reciprocal. Antenna gain works for both receive and transmit. So before you get an amplifier to increase your signal, you're better off getting a big antenna, because an amplifier only works on your transmit and you can out-talk your receive. On VHF and UHF, if a direct signal path is blocked, a beam antenna can be used to aim the signal at a reflecting surface to bypass the obstruction. That reflecting surface may be a mountain or a building or some other such thing that may be out there. So in general, you point your antenna in the direction of best reception, even if that's not the direction of which you need to be talking, and that reflection will help you in both directions. On VHF and UHF, if a direct signal path is blocked, a beam antenna can be used to aim the signal at a reflecting surface to bypass the obstruction. Most widely used type of beam antennas are Yagis. They were invented in the 1920s by doctors Yagi and Uda in Japan. Yagi beam antennas have much more gain than omnidirectionals in their preferred direction. This is our horizontal radiation pattern of a Yagi antenna. The radiation pattern of a typical 3-element Yagi antenna with a directive element, reflector, driven element, reflector, and director shows that most of the antenna's energy is focused in one direction along the boom. Of the antenna along the 180-degree axis of the graph, smaller amounts are radiated toward the sides and the back. This antenna also rejects noise and interference from the sides and the back. The round pattern of the isotropic antenna and the figure 8 pattern of a dipole are included for reference. And you see the dashed line is the round pattern of the isotropic, and the little tiny dotted line in there is the figure 8 pattern of the dipole.
So what would you say is the dBi of this Yagi?
That thing could be in the neighborhood of 8 or 9, I believe. Quite often, let's see. if we look at that, that says that, 3, 6, 9, 12, 18, 24. But I'm still thinking that's somewhere in the neighborhood of, if we say 3, 6, 9, but I think generally 3-element Yankees are somewhere about 9 dB.
Yeah, Howard, I'm looking at the box mine came in,
Yeah,
and on 2 meters, it's 9.5 dBi.
yeah. So that's referred with the isotropic source, like the light bulb we were talking about.
Yeah. I think in reality it's probably closer to 6, but that still takes my radio and about doubles what it looks like it's putting out in the direction that antenna's pointed.
Yeah.
People behind me are not going to hear me very well.
And you don't hear the people behind you very well. So that,
No, I don't.
all right, Yankees continue. Horizontally polarized Yankees are usually used for long distance communications. This results in lower ground losses when the wave reflects from or travels along the ground. As frequency increases and the size of Yagi elements becomes smaller, it becomes more difficult to construct practical antennas. Above 1 gigahertz, dish antennas become practical. And over on the right, figure 4.14, NCFO's dish antenna operates at 10 gigahertz and is portable enough to be taken on contest outings. And you, with a good dish antenna like that, you may be able to get close to 20 dB a gain. And if you know that 20 is 200 times what you put into it, that's quite useful. Other numbers you don't need to know, but you'll want to later. Which of the following describes a simple dipole oriented? I'm sorry, reading the wrong one again. Which of the following describes a type of antenna loading? Electrically lengthened by inserting inductors in radiating elements. And if you remember, they said that inserting or coiling the wire, making an inductor, is called loading. So that's A again. Which of the following describes a simple dipole oriented parallel to the Earth's surface? And that would be a horizontally polarized antenna. What is the disadvantage of the short flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter wave antenna? And the answer is A, it has low efficiency. Which of the following increases the resonant frequency of a dipole antenna? The answer is C, shorting it. What is the disadvantage of using a handheld VHF transceiver with a flexible antenna inside the vehicle? A, signal strength is reduced to the shielding effect of the vehicle. What is the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? The answer is C, 19. What is the approximate length in inches of a half wavelength 6-meter dipole antenna? Answer again is C, 112 inches. In which direction does a half-wave dipole antenna radiate the strongest signal? And the answer is D, broadside to the antenna. What is an advantage of a 5/8 wavelength whip antenna for VHF or UHF mobile service? Answer is A, it has more gain than a quarter wavelength antenna. What antenna polarization is normally used for long distance CW and SSB contacts on the VHF and UHF bands? Again, it's C, horizontal. Most of your FM with repeaters and such are done with vertical antennas, but when you're going for longer range and not using a repeater with CW and sideband, that antenna is turned to where it's an horizontal antenna. If it's turned to where the elements are up and down and it's vertical polarization, then that's when someone's mostly trying to use FM and operate with a repeater. When using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight path? And the answer is B, try to find a path that reflects signals to the repeater. I was visiting with a ham that lives north of Asheville in Madison County, on the side of Dogged Mountain. And he said in order for him to work into the Mitchell repeater, which is almost due east of him, he pointed his antenna almost directly north and reflected off the mountain. And that's how he did it regularly or most all the time. So that's where they're talking about in the B, try to find a path that reflects signals to the repeater. What is a beam antenna? And the answer is C, an antenna that concentrates signals in one direction. Which of the following types of antenna offers the greatest gain? Now, this is something we hadn't talked about before. And the answer is D, the Yagi. All those, all except B, are real antennas. B, again, the isotropic antenna, is perfect and that's not available. Practical feed lines and associated equipment. Let me take about a minute break and go get some more water. I'll be right back. Talk among yourselves.
All right, I have a question. When the equation used to determine the length of your half wave or quarter wave antenna, that constant, what was it, 486? What is that and why?
Okay, listen to my explanation and promptly forget it, because it is not the answer to a question on this test. You start out with the speed of light. Okay, which the formula starts out as a metric. You throw the unit conversion and get from meters to feet. And then when you take this, when the energy travels through a medium, it slows down. So they take the speed of light and you throw in a few percent reduction, it slows down. You look at the atmosphere. That affects it. The kind of wire has an effect on it. If that wire is insulated, that affects it. So that 468, Howard, they talked in that picture about going back to 490. That gives you a longer wire. And the practical thing is when you're building an antenna, all of us have a wire shortener. It's called a pair of side cutters or something like that, wire cutters. None of us have a wire stretcher. That's why you start out long. But that 468 number incorporates all of those little factors, and it is not a number carved in stone. It is a good guideline. Reality is when you put the antenna up, if you can get it high enough, and that is quarter wave is the recommended, which a quarter wave 160 meter antenna, none of us have poles tall enough to do that. So that affects how the antenna works because it's closer to the ground. But that 468 is just a good general guideline number. Don't think that it's magic. Don't think that it is carved in stone. Just remember if they ask you something about figuring an antenna length, 468 is a good number to remember for taking the test. 234 is just half of that. That's your quarter wave length. But again, it is not a hard and fast number. The speed of light in a vacuum is a hard and fast number. But when that waves moves into our atmosphere, it slows down a little bit. When it goes into our copper wire, it slows down a little bit. When we use insulated house wire, it slows down a little bit. And again, those are all some factors that you can figure in, but the better way to do it is start with the 490 number, put it up in the air, see what it does, and if it needs to be a little bit shorter, that's real easy to fix.
And funny enough, 490 is I think it's 493 is half
Yeah,
of what it comes out in metric.
yeah.
Okay.
Don't get hung up on that being a hard and fast magic number.
Well,
It's just a really good guideline.
Yeah, that's an excellent answer. Thank you.
And we all use it.
Yeah. All right. Practical feed lines and associated equipment. Common types of coaxial cable. RG6, 75 ohms. It's what you use for TVs. If you have cable, or you could use it to run to an external antenna. And you can see they talk about how much loss is in that is 1.4, that's dB per 100 foot. And that's at 30 megahertz. And at 150 megahertz, it's 33 dB. So 33 dB is an awful lot of loss. What would that be? 1/300th or a little less? But at any rate,
It's just a really good dummy load for 2 meters.
oh yeah. RG8 is its loss is 1.1 or 2.5 at 100 megahertz. All those are different types of coax with a little better or worse losses. In the thing that they pretty much have in common is all the ones that have lower loss are more expensive. But that's just kind of the way it is. The cheapest one you can buy is that RG6.
So
And
Outback,
if you happen to have an antenna that you want to use on 40 meters for receive only, it's fine. Because 1.4 dB down at those lower frequencies, that's, you can see, that's almost as good as what the RG13 213 is 1.1 dB, and LMR 400 is 0.7 dB. So for a receive only antenna, it would be fine, but it would be terrible at transmit. Okay. Coaxial cable called coax. See table 4.1. We just looked at that a lot. Performance of coaxial cable depends on the integrity of its outer jacket. Moisture contamination is the most common cause of coax failure. Prolonged exposure to the ultraviolet UV sunlight will also cause the plastic in the jacket to degrade, then cracks, then moisture. Some coax jackets use a pigment to absorb and block the UV. Coax should not be bent sharply. It can short center conductor to outer braid. And it may not do it right now, but over time that stuff can migrate to the outer if it's bent sharply. Coaxial feed connectors. And up there, you can see a lot of different connectors. And it looks to me like adapters there on the bottom end. The most common one that you'll see is the UHF connector, and that does not refer to its frequency. Back in, I guess, the 30s when they came up with it, they thought 30 megahertz was a very high frequency. So, but at any rate, that's just in general the ones you see. That F, that's the one on the back of your TV. The UHF, that's the one on the top there. There's the same thing. They're your common one that'll be on your radio. Some radios, if you get one that'll go up into the 400 megahertz range, so we'll use that N connector on the end. And there's a lot of adapters that are in there. UHF and BNC, you see those sometimes. The one that you see on most of your portables radios now is a sitting here looking at one. Harry, tell me. The connector on your handheld radios, however, there are two types of those that are common. If you have a Chinese radio, the one that's attached to the radio is a male connector. And it's an SMA male. SMA is the type of connector. And if you have a Japanese-made radio, it will have a female connector on the radio and a male connector on the rubber ducky that screws on it. So you cannot use, without an adapter, anybody's rubber ducky on your Chinese radio or vice versa. You have to pay attention with those because of manufacturer differences. Types of connectors to use depends on signal frequency. UHF series of connectors, the PL259 and the SO239 receptacles are the most widely used for HF equipment.
And here's a PL259.
Okay. Above 400 megahertz, the type N connectors are used. Water in coaxial cable degrades the effectiveness of the braided shield, and it increases the losses in the coax. In low loss air core or open cell foam coax, special techniques are required to prevent water absorption. SWR meters and watt meters. Figure 4.16, the SWR meter measures power flowing toward the antenna and toward the transmitter, reflected or reversed. SWR meters measure SWR by placing them in series with the feed line, usually right at the output of the radio. Many radios include a built-in SWR meter. Alternatively, a directional watt meter can be used to measure SWR. Measure power flowing toward the antenna and power reflected from the antenna by rotating a sensing element turning switch. And then you use a formula to get the SWR. Impedance matchers or transmatches or antenna tuners are used if the SWR at the end of the feed line is too high for the radio to operate properly. Connected at the output of the transmitter, adjusted until the SWR measured that the output is acceptably close to 1-to-1. Antenna system's impedance has been matched to that of the transmitter output. Most tuners combine the function of impedance matcher, directional watt meter, and antenna switch. Automatic tuners sense when SWR is high and make the necessary adjustments. Antenna analyzers. The popular MFJ series of antenna analyzer are used to adjust and troubleshoot antenna systems. The instrument contains a low power signal source with an adjustable frequency and an SWR meter. The LCD display shows the operating frequency and SWR and an SWR meter, as well as the D'Arceval meters on the front there. The LCD display shows the operating frequency and information about the antenna impedance. The meters show SWR and feed point impedance. Used to measure an antenna system without using a transmitter whose signal might cause interference. Practice questions. See how we're running here. Which of the following causes failure of coaxial cable? And the answer is C, rapid fluctuation in transmitter output valve.
Think you're looking at the wrong screen, Howard.
Yeah, the one I'm reading and the one over here. Well, no, I believe all those. That should have been all the above, it looks to me like.
Well, according to the screen I'm looking at, which is the one that you sending us, says the answer is A.
Okay, maybe I'm seeing something. Okay. Moisture contamination. Okay, I'll buy that. However, you can vouch that you can melt coax at 100% duty cycle. And I will correct myself in one more time. Which of the following causes failure of coaxial cables? A, moisture contamination. Why should the outer jacket of coaxial cable be resistant to ultraviolet light? And this one is C. Ultraviolet and RF signals can mix. No. What am I? This is D. Oh, I see what I'm looking at. It is D. Ultraviolet light can damage the jacket and allow water to enter the cable. What is a disadvantage of air core coaxial cable when compared to foam or solid dielectric? C. It requires special techniques to prevent moisture in the cable. Which of the following types of solder should not be used for radio and electronic applications? A. Acid core solder. What is the characteristic appearance of a cold tin lead solder joint? Cold joint is a bad joint, by the way. And the answer is C, a rough or lumpy surface. And those are corrected by remelting them. Which of the following RF connector types is most suitable for frequencies above 400 megahertz? The answer is B, type N. Which of the following is true of PL259 coax type connectors? They are commonly used at HF and VHF frequencies. C. Which of the following is a source of loss in coaxial feed line? Water, intrusion into coaxial connectors, high SWR, multiple connectors in the line. And the answer is D, all of the above. All these choices are correct. What is the electrical difference between RG58 and RG213 coaxial cable? Answer C. RG213 cable has less loss at a given frequency. I think it also probably has more power handling capability too. It's larger. Where should an RF power meter be installed? The answer is A, in the feed line between the transmitter and the antenna. Which of the following is used to determine if an antenna is resonant at the desired operating frequency? And the answer is B, an antenna analyzer. Which instrument can be used to determine SWR? The answer is D, a directional watt meter. What is the major function of an antenna tuner and antenna coupler? And that answer is A, it matches the antenna system impedance to the transceiver's output impedance. And then by meaning the antenna system, that includes the coax. And that's it.